If you have ever ridden a bike, you'll know it's very difficult to start pedaling in a high gear. So we need to start in a low gear to get the bike moving. At a certain point, our legs are spinning very fast, but we can't go any faster. So we need to change to another, higher gear. Once we reach a steep hill, we need to move to a lower gear. The same with a car. We start in our lowest gear number and work our way up as the vehicle increases in speed. Then we change down as we drive up a hill. A low gear provides low speed but high torque. A high gear gives high speed but low torque. Torque is a measurement of the force which causes something to rotate around a point. Think of a wrench and a nut which is seized up. Using a small wrench is very hard to free the nut. Using a long wrench will make it much easier. That's because of torque. If we used a 30 centimeter wrench and applied 90 newtons of force, we have 0.3 meters multiplied by 90 newtons, which gives us 27 newton meters of torque. However, if we applied the same 90 newtons of force to a wrench that was 60 centimeters long, then we would get 0.6 meters multiplied by 90 newtons, which gives us 54 newton meters. So from this simple formula, you can see we have more force acting on the nut by using a longer wrench. Essentially, we're using a larger circle to turn a smaller circle. By changing the size, we change the speed and the torque. If we were to connect two gears and rotate one of them, then the other gear would also rotate. If we attach the engine to the first gear, then this will be the driver gear, and the other gear is therefore the driven gear. When the two gears are the same diameter, we have a 1-to-1 ratio, which means every time the driver gear completes a full rotation, the driven gear also completes one rotation. So the output speed is the same as the input speed. If the driven gear is half the diameter of the driver gear, then we have a 1-to-2 ratio, which means for every full rotation of the driver gear, the driven gear completes 2 full rotations. This means the driven gear is rotating much faster. If the driven gear is twice the diameter of the driver gear, then we have a 2-to-1 ratio, which means for every 1 full rotation of the driver gear, the driven gear rotates only half a turn. So we need the driver gear to rotate twice to complete a full rotation of the driven gear. Notice that the driven gear rotates the opposite way. This is basically a reverse gear. In order to make the output rotate in the same direction as the input, we need to insert another gear which creates something known as a gear train. The middle gear is known as an idler gear. We could add many gears side by side to change the speed and also the output direction, but this will take up a lot of room. So instead, we can mount gears to the same axis and create a compound gear train. This will do the same job, but it will take up far less space. Let's look at how to calculate the RPM and torque of simple gear trains. By the way, you can download an Excel sheet of these calculations. Links can be found in the video description for those. We're going to use the formulas ratio equals teeth of the output gear divided by teeth of the input gear. RPM output equals the RPM input divided by the ratio. And finally, torque output equals the ratio multiplied by the torque input. For example, if gear A has 8 teeth and gear B has 10 teeth, the ratio is 10 divided by 8, which is 1.25. If gear A rotates at 150 RPM, then 150 divided by 1.25 equals 120 RPM. If gear A has a torque of 20 Newton meters, then 1.25 multiplied by 20 gives us 25 Newton meters. This gear will rotate the opposite way to gear A. It will rotate slower because it is larger, but it will have more torque. If we add gear C with 20 teeth, The ratio is 20 divided by 10, which gives us 2. The RPM output is 120 RPM from gear B divided by 2, which gives us 60 RPM. The torque is going to be 2 multiplied by 25 Newton meters from gear B. This will give us 50 Newton meters. So this gear will rotate the same direction as gear A, but it will rotate slower because it is larger, although it will have more torque. If we were to add gear D with 8 teeth, then the ratio is 8 divided by 20, which gives us 0.4. The RPM is 60 RPM from gear C divided by the ratio of 0.4, which gives us 150 RPM. The torque is 0.4 multiplied by 50 Newton meters, which gives us 20 Newton meters. So this gear will rotate the opposite way to gear A, but it is the same size, so it will rotate at the same speed and the same torque, although this doesn't take into account any losses which we would see in the real world. So this setup lets you visualize how gears manipulate speed, torque, and direction. What if we had a compound gear train like this, which has the same size gears, the same input torque, and the same rotational speed? Again, links in the video description for the Excel sheet calculator for this. So with this setup, we have 4 gears, A, B, C, and D, but B and C are compound. If gear A has 8 teeth and gear B has 10 teeth, then the ratio is 10 divided by 8, which is 1.25. Gear A rotates at 150 RPM, so gear B is 150 RPM divided by 1.25, which gives us 120 RPM. Gear A has a torque of 20 Newton meters, so gear B is 1.25 multiplied by 20 Newton meters, which is 25 Newton meters. So this gear rotates the opposite way to gear A. It will rotate slower because it is larger, but it has more torque. If gear C has 20 teeth, then the ratio is 20 divided by 10, which is 2. The RPM is going to be the same as B, which is 120 RPM, because these two gears are compound and share the same shaft. The torque is also going to be the same as B, so it's 25 Newton meters. This gear also rotates the opposite direction to gear A. It will rotate slower than gear A because of the size of gear B, and it will also have less torque than gear A, again because of gear B. If gear D has 8 teeth, then the ratio is 8 divided by 20, which is 0.4. The RPM is 120 RPM from gear C divided by 0.4, which is 300 RPM. The torque is 0.4 multiplied by 25 Newton meters from gear C, which equals 10 Newton meters. So this gear rotates the same direction as gear A. It rotates faster, but with less torque. So we need to consider the application of the gearbox, how many